Hello everyone. Today I am here to discuss another important topic of solid mechanics, that is columns and strut. In this lecture, I will discuss about the column, what is a column, how does it differ from a column, how does a column fails, what are the difference between the short column and the long column, then what do you mean by buckling load, crippling load, assumptions made in Euler's theory, stability condition, then determination or find the expression for crippling load for different types of end conditions. Now, any member subjected to axial compressive load. Any member subjected to axial compressive load is called a column or strut. A vertical member subjected to axial compressive load is called column. If the member is vertical and if it is subjected to axial compressive load, then we'll call it as column. The example is pillars of a building. An inclined member subjected to axial compressive load, always it will be called as strut. Means if the member is inclined and if it is subjected to axial compressive load, then we'll call it as strut. And apart from this, strut may also be horizontal member. Now see the last point, load carrying capacity of a compression member. Load carrying capacity of a compression member depends not only on its cross-sectional area, but also on its length and the end condition of the column. The end conditions will be different types of end condition. Both ends are hinged, both end fixed, one end hinged, other end fixed, like this. Now here you can see the difference between the beam, strut and the column. Column is a vertical member, strut is an inclined member, and again beam is an horizontal member, but loading is there. Horizontal member, but if there is a loading, then we'll call it as beam. Now the definition of strut, you can say like this, it is a structural member subjected to axial compressive force is called strut. It may be horizontal, vertical and inclined. But the cross-sectional area of the strut are very small. And also we can say strut carry smaller compressive load. It is used in roof truss and base truss that we already discussed in the analysis of truss. Then if you go for column, then it is when the strut is vertical. When the strut is vertical, it is known as a column. But its cross-sectional area is large. And normally columns carry heavy compressive load used in concrete and steel buildings. So these are the basic difference between column and the strut. If the question comes, what are the difference between column and the strut? So you have to mention these points. Now how does the column fail? Column will fail by direct and compressive stresses, that is direct compressive stresses, or the column may fail by buckling stress, or the column may fail by both direct and bending stress. Now, what is the short column and the long column? See the difference. When the length of the column is more as compared to its cross-sectional dimension, when the length of the column is more as compared to its cross-sectional dimension, it is called long column. And when the length of the column is less as compared to its cross-sectional dimension, it is called a short column. These are the mathematical terminology we will discuss later on in the next class. Okay, now what is a crushing load or crushing stress? If the compressive load on a strut, if the compressive load on a column, see, it is if the compressive load on a short column is gradually increased, means you are applying load to a short column and that load is compressive in nature, then a stage will reach, a position will reach when the column will be on the point of failure. Corresponding load is called crushing load. And crushing load upon the area of cross section is called the crushing stress. Then what is buckling and crippling? If the compressive load on a long column is gradually increased, then it will not fail due to crushing alone. If the column is long and you are applying load which is compressive in nature, then the column will not fail due to only crushing load, but also due to bending also. The load at which the long column bends or buckles is known as buckling load or critical load, or you can say crippling load. A long column will fail when maximum stress, that maximum stress direct plus bending stress is more than the crushing stress. Means for long column will bend, long column will fail by the application of both direct and the bending stress. Now these are some assumptions made in Euler's theory. The first one is the column is initially straight, means it would not be bent. The cross section of the column should be uniform. The line of thrust coincides exactly with the axis of the column, means the load that you are applying, it must be with the axis of the column. The material is homogeneous and isotropic. The shortening of column due to axial compression is negligible. So these are some assumptions normally it is asked in the examination. Now for long column fails because of the direct stress and the bending stress that we already discussed. Suppose sigma d is a direct stress and it is equal to P upon A. This is a column and you are applying a load here, P, the compressive load. So P upon the cross-sectional area is the direct stress. And what is bending stress? It is P into Y by Z, where P is the load, Y is the distance from the central axis, or this is the Y distance, and Z is the section modulus. But from bending stress theory, what we know? M by I is equal to sigma B by Y. So sigma B is equal to M into or M by Z. I by Y is Z. Maximum stress is direct stress plus bending stress. Minimum stress is direct stress minus bending stress. Okay. Now some sign conventions that we have to take for convexity. It is convexity. That is, the nature is convex in nature because of the application of the compressive load. Then we will take it as positive. And if it is if the nature of the buckling is concave, that is concavity, then we will take it as negative. Now I am discussing here the first end condition, that is both ends of the column are hinged. This is the first end condition. Both ends of the column are hinged. So if the both ends are hinged, see, then there will be only one compressive load. Hinged means one horizontal load, one vertical load. So the horizontal load here and the horizontal load here, it will balance each other. So we will have only compressive load at the two ends. So only P load is there at the point A. Both A and B are hinged. Both A and B are hinged. The length of the column is L, and this is the deflection Y. Upon the application of the compressive load, the deflection is Y, and I've taken this section at a distance of X from the end O. So we know already from the deflection of beam chapter, the equation of a curve is M is equal to EI d2y dx square. This M is equal to EI d2y dx square. That we know already from the deflection of beam chapter. Now here, what is the moment M? M is P multiplied by Y. M is P multiplied by Y. P, line of action is P is E, and we are taking moment at this point. Moment this point. So P multiplied by Y is the moment, and because it is nature is according to the nature in our sign convention, it is negative, so it is minus py, concavity in, so it is concave nature, so minus py. Now this is the equation ei d2y dx square is equal to minus py, or you can say ei d2y dx square plus py equal to 0. Okay, so the equation can be written as d2y dx square plus alpha square y equal to 0. d2y dx square plus alpha square y equal to 0, where alpha square equal to p by ei, means I have divided this whole equation by ei. So alpha square d2 square d and d2 square y by dx square plus p upon ei. So p upon ei, this term we have taken it as alpha square. So the equation is d2y by dx square plus alpha square y is equal to 0. This is the differential equation. Now we have to solve it. So differential equation is this. Differential equation is this d2y dx square plus alpha square y, where alpha square is equal to p by a. And what is solution? The solution of y is a sine alpha x plus b cos alpha x. That you have to remember it. In mathematics also, in the differential equation, you have solved this problem. The equation of this equation, this differential equation, is y equal to a sine alpha x plus b cos alpha x. Now at x is equal to 0, y equal to 0. How? At x is equal to 0 means you were talking about the fixed endpoints, hinge endpoints. Here the deflection is 0. So if I put this values, x is equal to 0, sine 0 0, cos 0 1, y 0, so b is equal to 0. If I put this condition, boundary condition, at x is equal to 0, y equal to 0, b equal to 0 in this above equation, then I will find b is equal to 0. Now second end condition is x is equal to L, y equal to 0. X is equal to L, y equal to 0. If I put this condition, x is equal to L, y equal to 0 in the equation, in the solution, y equal to a sine a alpha x plus b cos alpha x, then what will happen? You see, y equal to 0, and here already b 0, means this term is 0. So here it will be a sine alpha L, a sine alpha L equal to 0. So if a is equal to 0, y is 0. If a is equal to 0, y is 0. How? Because already we have seen b is 0. So in this equation, if a is 0, then y will be 0 for all values of load, and there is no bending, which is not true. So that means the sine alpha should be equal to 0. That means the sine alpha should be equal to 0. And if sine alpha equal to 0, then what is the value of sine alpha equal to 0? No, sorry, sine alpha equal to 0. So alpha is equal to pi, considering the least value, or alpha is equal to pi by L. If alpha equal to pi by L, then I can say Euler stripping load is equal to alpha square multiplied by EI. Alpha square multiplied by EI, and alpha square is equal to P by EI. Okay. What is alpha? Alpha is pi by L. Alpha is pi by L, so it is pi square EI, pi square EI by L square is the crippling load for this end condition. PE is equal to alpha square EI, because here alpha square is equal to P by EI. P is the crippling load. P is the crippling load. You see, we have taken this alpha square is equal to P by EI. So P is equal to alpha square EI. So here I have written P is equal to alpha square EI. And what is alpha? Alpha is pi by L. So square it, so pi square EI by L square. So this is the expression for crippling load for the end condition of the column. The end condition is both end hinged. So with this, I have completed this topic. If you find my video suitable, workable, and please share it, like it, and subscribe my channel.